Hello, this video looks at the structure of the atom in brief. Now, let's begin with the basic definition of what an atom is. An atom is the smallest part of an element that can exist. And we are supposed to know the various subatomic particles of an atom. So let's start with this one, that we have the subatomic particles. An atom consists of protons, neutrons, and electrons. So these are the three subatomic particles of an atom: protons, neutrons, and electrons. Now, with that being said, let's look at the structure of an atom. An atom consists of a central portion which contains protons and neutrons. So here we got our nucleus here, which contains the protons, which I'm indicating with red color, and neutrons. Now, surrounding the nucleus are the electrons, which orbits in shells around the nucleus. So we got our shells here, and we got the electrons orbiting in shells. Okay, so we got our shells, the nucleus form the central portion, and within the nucleus we got our neutrons and our protons. Okay, we are supposed to also know that the bulk of the atom is concentrated in the nucleus. Most part of the mass of the atom is in the nucleus. Okay, so that is the general structure of an atom. The central portion called the nucleus, which contains protons and neutrons, and surrounding the nucleus are the electrons, which orbits in shells. Now, the specification requires us to know the charges and the mass, relative mass of the three subatomic particles. So let's go ahead and summarize that in this table. So here we go, our particles: protons, neutrons, and electrons, and their relative mass and charges. So protons have relative mass of 1, and the charge of a proton is positive. Now, neutron has relative mass of 1, and neutrons is generally neutral. It doesn't have any charge. And electrons have mass of 0, and electrons are negatively charged. Okay, so a recap: protons has a mass of 1 and is positively charged. Neutron has a mass of 1 and is neutral charge. Electrons have 0 mass and they are negatively charged. Okay, you got to remember this. We will use this in subsequent calculation. Now, another keywords, that there are some keywords that we got to know about atoms. And one is the atomic number. The atomic number is the number of protons in the nucleus of an atom. Now, the number of protons is equal to the number of electrons. It's very important you remember this. Now, what that means is that, let's go back to our model. So here we go, our nucleus. We are saying that the number of protons is equal to the number of electrons. The atoms therefore have neutral charge. What are we saying? Now, if you come to our model here, we got 1, 2, 3 protons. Now, we've just said that protons have positive charge. Now, we also said that electrons are also negatively charged. What we are saying here is that the number of protons is equal to the number of electrons. Therefore, let's go back here. We got 1, 2, 3 protons. Now, let's check the electrons. 1, 2, 3 electrons. So, in every atom, the number of protons is equal to the number of electrons. What that means is that the overall charge of the atom is 0. Now, because if you have 3 protons, which is positively charged, and 3 electrons, which is negatively charged, the protons charges will be cancelled out by the electron charges, and therefore the overall charge on the atom will be 0. Remember this. You will use this and understanding to do some calculations going forward. Now, the next thing you have to know is mass number. And mass number is the sum of protons and neutrons. Okay, the sum of protons and neutrons. Remember, we said that the bulk of the mass of an atom is concentrated in the nucleus. Therefore, if we want the mass of an atom, we have to add the proton numbers to the neutron numbers in order to work out the mass of an atom. Now, what that also means is that if we know the mass number and either the proton number or the neutron number, we can rearrange the equation and find the other subatomic particles. For example, the number of protons equals to mass number minus number of neutrons. So if we know the mass number and we know the number of neutrons, we can work out the number of protons. Okay, again, we can also rearrange the equation and find the number of neutrons if we know the mass number and the number of protons. So the number of neutrons is equals to mass number minus number of protons. Okay, so mass number is protons plus neutrons, and that will give you mass number. Neutron number is mass number minus proton number, and number of protons equals to mass number minus number of neutrons. Pay attention to this. You've got to take note of these formulas going forward. We will use it to do our calculations. Let's look at an example here. A potassium atom has atomic number of 19 and mass number of 39. Give the number of protons, electrons, and neutrons in the atoms. Okay, so here we have our mass number. Okay, mass number equals to 39. The number of protons that they want us to work, and you got the atomic number. Atomic number is being given as what? 19. So we know our mass number, we know our atomic number. Now we are required to determine the number of protons in this atom. We don't know. They also want us to find the number of electrons in the atom. We also don't know. Okay, and the number of neutrons. So we know the mass number and we know the atomic number. Now, how do we get the number of protons? We know from our definition that the number of protons is what? The atomic number. And so straight away, we know that our atomic number is 19, and therefore the number of protons will be what? 19. Now, knowing the atomic number and knowing the number of protons allow us to determine the number of electrons, because we have just said that the number of protons is always equal to the number of electrons in an atom. Remember, we just said that. Therefore, if we know the number of protons, we can find the number of electrons, because the number of protons is always equal to the number of electrons in an atom, and therefore the number of electrons in this particular atom will also be 19. Now we have to find the neutrons. Now from the previous equation, we know that mass number is equals to proton number plus what? Neutron numbers. Now here we know our proton number to be 19. We also know our mass number. If mass number equals to proton number plus neutron number, then neutron number will be equals to mass number. Remember, I just gave that formula. Minus our proton number. So let's go ahead and put the figures in. Our mass number is 39 and our proton number is 19. Okay? Now if we work that out, what are we going to get? We're going to get 20. So the number of neutrons, therefore, number of neutrons in this particular atom will be equal to what? 20. So that's how you work around the mass number and the atomic number to find the electrons and the neutrons in a particular atom. Okay, now with that, let's look at the let's go back to our previous screen. Let's look at nuclear symbol. Now, the atom of every element is normally represented by a symbol, and from the symbol you can determine the atomic number and the mass number of that particular atom. So here we got our generic atom is normally represented by this nuclear symbol, and you will see two numbers here. The bottom number, which is the B, is the atomic number. Okay, the bottom number is the atomic number and the top is the mass number. So when we write the nuclear symbol of any atom, the bottom number is the atomic number and the top is the mass number. So let's look at an example here. We got our potassium here. Potassium has 19 atomic number and the mass number is 39. The previous example we looked at, that's the potassium. So we have atomic number should be 19 and mass number is 39. Another one we've been given is hydrogen. If you look at the symbol, the bottom number is always given as the atomic number and the top is mass number. So here with this symbol of hydrogen, hydrogen has atomic number of 1 and mass number of 1. Now the next one is sodium. The bottom number is 11 and the top is 23. What that means is that the atomic number of sodium is 11 and the mass number is 23. So that's how we represent other atoms. Now if you have, you can pause the video and write the nuclear symbol of any other atom you know. Okay, now let's continue with isotopes. Isotopes are different forms of the same element which has the same proton number but different neutron numbers. Okay, isotopes are the same forms of the same element which have different proton number, i.e. different atomic numbers, and they have the same atomic numbers but different neutron numbers. Let's look at example. A common isotope that you come across is carbon-12 and carbon-13. Now let's look at their nuclear symbol. We got here carbon-12 and carbon-13. Carbon-12 have atomic number of 6 and mass number of 12. Now what that means is that the number of electrons in this carbon-12 is 6, the number of protons is also 6, and the number of neutrons is 6. Now let's come to carbon-13. The number of the atomic number is also 6. Remember, isotopes are atoms of the same element which has the same number of protons different neutron numbers. Now, what is the implication of the different neutron numbers? The differences in the neutron number result in differences in mass numbers. So here we have carbon-13, we have 6 electrons because the atomic number is 6. Remember, the number of protons is always equals to the number of electrons. So therefore, if our atomic number is 6, the number of electrons will also be 6. So the number of electrons is 6. If the number of electrons is 6 and the atomic number is 6, and we have a mass number of 13, the number of neutrons will be mass number minus the atomic number, and that should be 7. Now, what do you notice here? You see that both of them are carbon. They have the same atomic number, but their neutron numbers in carbon-12 is 6, and the neutron numbers in carbon-13 is 7. Now, it is these differences in neutron numbers that is resulting in different mass numbers. Okay, so that is a typical example of isotopes. Now let's look at chlorine. We also have chlorine-35 and chlorine-37. These are also different types of isotopes you come across, and chlorine-35 have atomic number of 17, chlorine-37 also have 17. They will therefore have different neutron numbers, okay, and therefore have different mass numbers. Okay, now let's look at another key term that you have to know about atoms: relative atomic mass, which is represented by AR, relative atomic mass, and it is the average mass of one atom of an element that is compared to 1/12 the mass of one atom of carbon-12. Okay, the definition you must know: relative atomic mass is the average mass of one atom of that particular element compared to 1/12 the mass of one atom of carbon-12. Now, there are certain particular formula that we use to work out the relative atomic mass of atom. Now, because atoms do exist as isotopes, remember we just mentioned isotope as different forms of the same element, for example carbon-12 and carbon-13. It means that if we want to look at for their atomic masses, we have to use the average masses of the individual isotopes in order to come up with their atomic masses. So therefore, we have to take an average of the masses. If an atom has one isotope, we use only the atomic mass. However, if an atom has one or more isotopes, we have to work out the average of the individual mass and take into consideration the relative abundance of the isotopes. For example, let's look at the different isotope for an element occurs in different quantities. So for example, if we go back here, carbon-12, for example, it is very likely that if you come across carbon, maybe 70% of the carbon you will see will be carbon-12, and 30% of carbons in existence will be carbon-13. And therefore, when we are looking out and working for their relative atomic masses, it's important we take into consideration their relative abundances, and therefore we use this formula to work out the relative atomic mass of atom. The relative atomic mass of atom is the mass of isotope 1 times its relative abundance plus mass of isotope 2 times its relative abundance divided by the sum of the abundances. Okay, so if an atom have, let's say, 2 isotopes, you take the first isotope, let's say carbon-12 and carbon-13. 10% of the atom you come across is carbon-12. Multiply 10 by carbon-12, and 90% of carbon you come across is carbon-13. Multiply 90 by 13, and then what you do is that you then divide that sum by the sum of the abundances, which in most cases will be 100. Let's look at an example here. So here we've got boron. Boron has two isotopes, boron 10 and boron 11. Now, given that the relative abundances of boron 10 and boron 11 is 4 and 16, calculate the relative atomic mass of boron. Okay, so here we have two isotopes of boron, boron 10 and boron 11. Okay, and we've been given the relative abundance of boron 10 and 11 as 4 and 16, and we are required to work out the relative atomic mass of boron. Now let's go back to our formula. Mass of isotope 1 times its relative abundance plus mass of isotope 2 times its relative abundance divided by the sum of the abundances. So let's look at the mass of isotope 1. Now isotope 1 is boron 10. Yeah, and isotope 2 is boron 11. Great. Now, what is the mass of isotope 1? The mass of isotope 1 is 10, and the abundance of isotope 1 is 4. The abundance of isotope 1 is 4. So let's apply the same principle. Mass of isotope 2 is 11, and relative abundance of isotope 2 is what? 16. Now, so let's go ahead and put this in the equation. Now, what is the sum of the relative abundance? The sum of the relative abundances equals to 4 plus 16, and that should give us 20. Okay, so let's go ahead and plug this in our equation. Our equation is mass of isotope 1 times its relative abundance. So what is the mass of isotope 1? We said the mass of isotope 1 is 10. So we have 10 times its relative abundance is 4. That's 4. And that is added to the mass of isotope 2, which we said is 11. So that's 11 times its relative abundance, we said is 16. And then let's go ahead and divide this by the sum of the relative abundances, which we have already worked out to be 20. So let's put 20 here. Now, what do we get here? We're going to get 216 and then divided by 20. And so therefore the relative atomic mass will be 10.8. Okay, so that's how you work out relative atomic mass if you know the individual isotopic masses and the relative abundances. Okay, that is the end of the video.